We have been undergrads together, engineering. And this guy has a degree in civil engineering. You know that. And Pedro Diaz from MNCC. And, the idea here is to share with you what we have been done on the simulation of stabilized finite element simulation for gravity currents. Point of view here is computational science engineering. The idea is to show you a lot of computations. Okay, so outline here is some introduction and motivation why we are studying this. The governing equation in our finite element formulations. Some numerical examples. We're going to restrict ourselves to the infinite volume 3D lock exchange configurations, a cylindrical configuration, which is very interesting because it's very challenging in terms of computing. And what we've been doing lately with my student Andre Rosa, which is seated up there, is adaptive mesh refinement and coursing for the lock exchange configuration. And then some conclusions and discussion to close my talk. What are gravity currents and why do we study them? This picture here shows from an experiment actual experiment from a sediment for a gravity current on a lock exchange from Brito. It has been doing in the university here in Brazil. Gravity density current is the flow with one liquid, but in another caused by the density difference between the two fluids. There may be several causes of this density, different composition, salinity, and temperature variations, and also can carry suspended particles causing that difference, which is resulting particle-driven gravity current, which calls important phenomena in geology with the turbidite flows. Sediment can form deposits for hydrocarbon and over geological ages, and this catastrophic event can carry sediment for hundreds of kilometers. There's evidence of this about geology, and all those things are happening maybe right now. I don't know. This is from Professor Parker from the University of Illinois Urbana-Champaign. This happens in geological time, the formation of canyon, the fan, and also the formation of canyon. So, if you assume that the model we're going to use describe this phenomena, this happens in geological time, and then that's why we study them. Oops. Motivation is sand deposited by this mechanism. The turbidites host a large amount of hydrocarbons reserves around the world, and particularly here in Brazil are the most major responsible for the current Brazilian reserves. I'm not talking about, I'm assuming that most of you heard about the huge pre-salt deposits in Brazil. I'm not talking about this. I'm talking about what is being exploited today. Not what's going to be exploited, but what we have today. Sands deposited by those currents encompass a family of deposits with some common characteristics, but very important distinguishing features. Geometries, granulometry, and can vary a lot. And they have complex interrelationships between the current dynamics, seafloor irregularities, slope, sediment supply, etc. And the design of well placement to optimize hydrocarbon production is very much dependent on those characteristics. And modeling this process, believe me, nowadays is most sensible steps in our hydrocarbon production project. If I may return, here. Actually, you see here, one of my former students, it's a geologist. He's trying to do some stuff on this. Actually, he's doing this stuff for Petrobras, the Brazilian oil company. So the focus of my talk is to investigate the applicability of stabilized finite element methods to study dynamics of gravity currents. The flow is dominated by Kelvin-Helmholtz instabilities at the interface between the heavier and the lighter fluids, and 3D lobe and cleft patterns. There has been a lot recently from a lot amount of work. Direct numerical simulation using pseudo-spectral method in 2D, 3D, etc. Particularly this Cantero in 2006 and 2007. Those simulations took months at the National Center of Supercomputing Application at the University of Illinois in Urbana-Champaign. So it's very fine mesh size. Also from guys from the ocean community, ocean simulation, oceanography community, using DNS, large edge simulation, etc. Some large edge simulation, pseudo-spectral methods from Professor Myburg, University of Santa Clara in the U.S. The group from Iowa with the finite volumes, with the strong, very high resolution simulations. And very recently appeared adaptive mesh refinement course and solutions. O'Callaghan is from the group from the Jerry solvers that use quadratrees and Cartesian meshes to solve this. And Hister is from the Pigot group in UK. There's an ocean research, a paper in 2011, Journal of Geophysical Research, and they use some sort of finite elements with triangulations, but they are restricted to 2D. Today, I'm going to show you preliminary 3D simulations with adaptive mesh refinement and coursing. Oh, well, this is the governing equations. I will present this in the large edge simulation of future Navier-Stokes equations, with as Magrinsky viscosity here, and the density transport equation also in the setup of large edge simulation. The details of those equations are in the reference here. Basically, it's coupled Navier-Stokes with some transport which represented the density difference or temperature, and we are under Wilson-esque assumptions. So the density difference are small, basically. The scaling parameters and non-dimensional group with the relevance is, the relevant velocity, the non-miniaturization of densities, pressure, the Reynolds numbers, which is basically the square root of the Grashof number, and the Schmidt number. And we also assume subgrid scale edge viscosity and diffusivity for the Navier-Stokes, and also for the density transport equations. This is a simple model, and then we have Muscal and computations and approximation of this into several possible ways. Okay, oops. Right. Now we use finite elements. Finite elements are unstructured grid methods, and there's a particular form for the finite element formulation, which is stabilizations. I mean, this is the Galerkin part, and we add several stabilization terms. What is interesting here is understand this stabilization for finite elements has been around for a while. And what is important for you to know now that stabilizations allow us to cope with spurious oscillations for a high Reynolds number, allow us to use equal water interpolation for velocity and pressure, okay, which is important in terms of discretizations. And everything here, stabilization, are variationally consistent. If we plug into these equations, the solution, the true solution, all the stabilization terms will vanish. And we are considering Magrinsky's model here as an artificial viscosity, which in some cases are important. So far, for the three-dimensional Navier-Stokes equation, again, I mean, U is the velocity, P the pressure, etc., etc. And this is constitutive equation for the fluid we are using under the usual assumptions. And this is for the transport, where I use the variable phi to represent the density difference or the temperature with it, or salinity. That depends on the physics we are looking at. And again, this is a stabilized finite element formulation where you have a discontinuity capturing the streamline upwind Petrov-Galerkin correction that gives you control along with the streamlines of this solution. And again, this is variationally consistent. Oops. Right. There's a technical side here that for the transport, we use this, which is basically a residual Bayesian. But look at these equations. This is just a residual scaling, which is somehow based on the element residual, the finite element residual. Somehow when you have when they're using dimensional quantities, you have to scale the residual. But here we are in the non-dimensional realm, and then this relies on the standard form for this discontinuity capturing for transport. How do we advance the equations? We do segregated time-marching, so we solve the three-dimensional Navier-Stokes equations, solve the transport. If needed, we adapted the time step. Why I quoted here? Because in the computational point of view, nowadays, our view here, I'm a co-author of this paper, advancing the solution on a PDE and pick up the time step can be regarded as a feedback control problem. Those two papers address this, and we can also control the time step or indirectly. If this is a unstructured grid, perhaps it's better to control and impose a CFL. Maybe if even the solution time marching is completely implicit. We prefer to control the CFL, and we look at this as a proportional, integral, and derivative feedback control problem to advance the solution in time. So this is more technical details on those papers here. So far for the numerical examples. First, we're going to consider two cases. As I said, the infinite planar lock exchange flow. We have a lighter fluid up and dense the fluid. We have a gate position, release the gate, whoosh, and we have the movement. Okay, this is interesting. There is a lot of experiments and a lot of data here, and there's the radial configurations. Those are the sketch of a radial configuration with trying to be axisymmetric, but it's not that much.
So there's a gate right there. The gate is right there.
Yeah.
So what is this white?
Because you release the gate, and then there's the two fluids move like this.
Okay. After
yes, move like this. Okay. It's typical for people who do the experiments, but in theory it's like this. But maybe in many times you have just one lock, right, and do the denser fluid supply like this. Yes, in one direction only. Okay. Okay. This is a picture of one of our simulations. Here is the mesh data. And here are some technical details. Our simulation codes rely on a lot of inexact Newton methods. We linearize the Navier-Stokes equation and use the inexact Newton method. The inexact Newton method is a clever association between Newton and Krylov solvers, where you pick the tolerance for solving your nonlinear problems and adapt it towards the convergence for the nonlinear problems at each time step. And of course, we use GMRes as a linear solver. And for the transport, this is the data. And then this is a picture of releasing the gate. And yes, releasing the gate, and you have this setup. You see a formation of Kelvin-Helmholtz, the nose, this strong boundary layer here. And, here's just a comparison for Grashof 1.5 to the power 10 to the power 6 and Schmidt number 0.71. Here are the solutions of DNS spectral 4.25 million of grid points. Harter, Mayburg, and Necker. See this high resolution here. This is a Cantero Journal of Applied Mechanics, 1.7 million of grid points. And how we do with 500,000 of grid points within the realm of large edge simulations. Not bad. The idea here is not to capture the small features, but even capture the larger scales. Look, we are thinking about geological time scale into this turbidite setting. So we need to know the global features and the global dynamics, basically. That's what's possible to get with large edge simulation. This is a movie that represents the solution. You see the formation of the lobes, clefts, and the evolution of all this complex dynamics. And here, how we compare. This is the head position, which is one of the main targets of our study here. It's for no slip boundary condition. Our solution sits here. And the red square is 2D large edge simulation, blue circles, 3D large edge simulations. And here we have the finite volume solution of UI in 2006 with 26.7 million points at the University of Iowa. Well, not bad for this low resolution, at least for this global feature. And we got this particularly, we are particularly happy with this solution. We have a plug-in Smagorinsky or the least square comprehensively constrained and discontinued with full residual, only at the vector residual. What I'm saying here is some particularities from the stabilized finite element solution can, change resolution. Particularly this is so dissipative that we are losing some characteristics on this dynamics. And they also have a impact into the run. This computation had been done in 2007 with a moderate number of CPU, I guess 16 cores basically. And since we are controlling adaptability time step, the time step is not, the number of time steps not the same. But you see that we solve the nonlinear problems at each time step very fast and very quickly. Okay?
Can I ask a question?
Sure, please, go ahead.
So those first billows that you see there, these are truly billows, right?
Yeah.
But these are not. If you wait long enough, will you see it billowing or just...
You're going to see, we don't have enough resolution to see. Then when you do adaptive mesh refinement course, you're going to see this billowing.
Well?
Yes. We're going to show up. Okay, this is a problem of resolution that I will address later. That's why we're going to do adaptive mesh refinement in coursing. Right? This is a fixed grid computation. Let's see the more interesting, the cylindrical configuration here. That's a number of nodal points, elements, etc. And just release this in this cylindrical configuration. You're going to spread out like this. One point that is important in some of DNS, 3D DNS simulation reviews, that due to the flow characteristics, the number of lobes and clefts that advances here remains constant. Okay? And we're going to see this, but due to our lower resolution into our large edge simulations computation, the number of lobes and clefts we got are smaller than the high resolution, highly resolved DNS computations we are taking as reference. Okay? See, a DNS spectrum with 28 million of grids, they have much more resolution here. If you count this, the number of lobes and clefts, this remains constant, and remains constant in our simulation with half a million grid points. Okay? Details on the paper, I will let you know the paper later on, but the details are there. I believe that the guys count something around 14 to 15 lobes and clefts, and we got 9 to 10 but we are capturing the physics since the advance is exactly remains constant. The advance of lobes and clefts remains constant. This is the head position compared to the 3D or highly resolved DNS simulation for the same parameters. And this is a movie. We did 1/4 of this and rebate everything to get this nice movie here. Oops. Oh. You see that more or less remains constant. Okay. I like this movie. Let's see it again. Again? Oh. Again. So, you see, as you mentioned, we are losing some resolution, and instead of doing fixed grid computations, with my student that's going to finish in the next term, we start to do adaptive mesh refinement coursing. All the literature so far today on this, for this particular problem, are in oceanography. So the temperature is responsible for the buoyancy, and the couple is temperature. Okay, so we have advective transfer is temperature. We have the buoyancy dependent on temperature. We just drop the Smagorinsky under the idea that's not particularly laminar, but we don't have this need to add this additional viscosity. The mesh resolution will try to do the trick, and the physical conditions are adapted from the guys from the Pigo group, the Hister et al., which is published in the Ocean Research in this year. Those are the characteristics. And this is our slice. This is a slice. Here, it's not, you can't see, but you're going to see that we have mesh adapted in the slice. It's not 2D, but it's rather a 3D computations we are doing on a slice in order to try to best compare with the available on 2D only, the only available simulations so far, which are basically 2D. Right. This is a temperature captured by our adaptive mesh refinement course. See, look at the second one here that start to appear. Again, this is computational stuff. We do parallel adaptive mesh refinement course supported by the libmesh package. Has been under development at the University of Texas at Austin. We collaborate at the Institute of Computational Engineering and Sciences at UT Austin. We collaborate with this group. We do our developments with libmesh since basically around this 2006. It's C++ open source library. There's a lot of error estimators for computing this based on a flux jump between adjacent elements. We use only as an error indicator here the temperature gradient. The element error E has a normal probability density function between M and standard deviation S, like this. And user need to find the proper refinement and coursing factor to produce the best solution. And we have to implement all our stabilized finite element formulations into this package in order to inherit the parallel adaptive mesh refinement and course capabilities built in libmesh. Okay. Those are solutions. Here later on, you're going to see that it appears. Right? That answers you. At 2 time steps. Those are the boundary conditions. We are doing adaptive mesh refinement, as I said before, based on temperature fields. The error indicator is based on the temperature gradients. It's not clear at the moment that this will be enough. Probably due to these boundary layers around here, perhaps we have to look at error indicator to the Navier-Stokes equation. But so far, all the computations done before in 2D use only temperature. So it's something that we are investigating because there's some strong boundary layers occurring here. And maybe I'm going to need to look at Navier-Stokes equations, error indicator. And there's a movie here. Again, we're looking at the projection, but look, this is a slice on a 3D computation. Oops. You see the formation of the Kelvin-Helmholtz bills, the nose of the front. And we have resolution where we need to have. Again, this is, we should have stopped the computation before because there's no, but anyway. Adaptive mesh refinement course can follow all the features of it, right or wrong, but we should have stopped the simulation before. Let me remind you, this history here is the Ocean research paper published in 2011. This is the fixed mesh characteristic length of our computation is this. And for slipping, no slipping on the boundary of top, we compare our solution with the 2D solutions, which compares very nicely. And this is the fruit number, is the ratio between the front speed and fluctuation velocity, which is dependent on the gravitational effects. And again, we see basically here that the frequency that we update the mesh, which apparently we're going to play a very important role, doesn't change much the results. And we have a good, a good match with the 2D solutions. And I think that's it, right? I think about this, that's it. And is a comparison fruit number, the previous published results, those are the references, the Grashof number, and non-slip fruit and the free slip fruit. Our present on the slice is here, and you're going to see that we have a pretty good match, and there's experiments for higher Grashof numbers around this. And I mentioned before that there's another group that did computations with 2D, with the Jerry solver, the quad tree-based solver. It's published in Journal of Geophysical Research, and they say that adaptivity somehow slowed down the front compared to the DNS, which is basically the effect here and here compared to the DNS. And we are seeing this. And to end my talk today, we just say that we apply a stabilized finite element formulation to study dynamics of density currents, where turbulence is important. Fixed mesh simulations show that global flow features compares well with the previous detailed DNS and large edge simulations and experiments. There's a large room for improving turbulence modeling here. We are working with the new framework called VMS, the variation remote scale approach to turbulence, which is not basically different from the standard LES, which is basically modeling the extra term. Now we approximate in a consistent manner, in residual-based consistent manner, this extra term. We have our group have papers on this. This is for the basic stuff where we do comparison with DNS. This is for free surface flow, which is basically something that is related to this. We see that adaptive mesh refinement course allows representation of multiple scales, improve the resolution where needs, where Ricardo here went straight to the point. And we have seen good agreement between our present simulations, is a 3D on a slice, and other results, numerical experimental. Everything here, you see, is computed in parallel. Okay, parallel computing is pervasive here. And the present work is the first step towards simulation of turbidite currents, where we need to take into account seafloor irregularities, slope, sediment supply, other important parameters. Well, we have, this guy here is us, And this paper here is at the International Journal for Numerical Methods and Fluids. Paulo Paraíso, the geologist that worked with us now at Petrobras, you should take a look on his thesis. He used this to do some geological flavor computations, which were very interesting. Issues related to use to adaptive mesh refinement course and in parallel under this setting are being discussed in the recent paper that we published at the International Journal for Numerical Methods and Fluids this year in our group where we discussed this. And there's André Rosa sitting down there. He's finished his PhD thesis that he's doing the simulations. And next term, he'll be finished. And I hope that everything will go well. Thank you for your attention.
Any questions, comments? Here.
I have a couple. Can you go back to the, I think it was the last animation that shows.
Which one?
Yes.